So, the last class we talked about Riva's work and we concluded with Riva's work, where we talked about, if you remember, it was a very complex hybrid we talked about. So, I will just do a bit of a recap with the Riva's work, where we talked about the use of 3-markaptophenyl boronic acid, gold nanoparticles, and glassy carbon electrode was drop casted with a bamboo like multi-walled carbon nanotube. So, basically it is a hybrid structure. On that hybrid structure, glucose oxidase was immobilized. So, today we move on to Turner's work. These are some of the prominent groups. Turner, on the contrary, utilized a much more clever strategy. He moved on to molybdenum sulfide. Those of you are aware about some of the 2D materials, while graphene is one of the 2D materials with some exceptional properties. A very closest relative of graphene with such unique properties is molybdenum sulfide, MOS2. So, exploiting the planar structure of MOS2, Turner did something pretty interesting, which I will be talking. Turner's group have demonstrated the formation of structured layer of gold nanoparticle on a 2-dimensional molybdenum sulfide nanosheet, which has gained attention very recently in the field of electrochemical biosensors as an ideal candidate matrix. Okay. Briefly, a dispersion of MOS2 nanosheet in PBS was prepared by ultrasonic treatment, and then dispersion by MOS2 was mixed with commercial 5 nanomolar diameter gold nanoparticle solution. By incubating the mixture at room temperature for 3 hours, what we get is molybdenum sulfide and gold nanoparticle self-assembled nanosheet. The resulting MOS2 gold nanoparticle were mixed with glucose oxidase. Now, again the same thing, glucose oxidase mixing and incubated overnight. The MOS2 gold nanoparticle and glucose oxidase hybrid structure was shown to have a sensitivity of 13.8 microampere. The developed biocatalytic interface based on 2-dimensional MOS2 gold nanoparticle has the potential to be used for the immobilization of biomolecules. This is Turner's work. So, if you look at it, we started with gold, then we moved to carbon, now we are into molybdenum sulfide. So, this journey is going on and on. Okay. Now, there is another very interesting development using zeolite. What are zeolites? Zeolites are hydrated aluminosilicates of the alkaline and alkaline earth metal. About 40 natural zeolites have been identified during the past 200 years. The most common are analcime, cabazite, aeronite, ferrite, hyaluronidite, so on and so forth. There are 3 main uses of zeolite in the industry: catalysis, gas separation, and ion exchange. So, most of the ion exchanger what you see in your house, especially the one which are used for water purification, they all contain the zeolites. Okay. A new method has been developed for the encapsulation of the gold nanoparticle and glucose oxidase together into the cavity of a zeolitic imidazole framework, which is called ZIF8. This study showed that ZIF8 is stable and provides a very large surface area, the unique cavity which can accommodate both gold nanoparticles and glucose oxidase. Furthermore, gold nanoparticles were found to promote electron transfer efficiently. I have mentioned this earlier, and the system due to their high conductivity, and for this reason authors claim that the incorporation of gold nanoparticle improved the sensitivity of the system tenfold. So, add to that list is now zeolite. with nanocarbon and its variations. So, you have carbon nanotubes, you have graphene, you have carbon quantum dots, we will come to all of them. So, one of the aspect of biosensor research you are realizing, it is closely integrated with the development or advancement in material science and engineering and chemistry, and specifically materials which has improved or improvised electrical conductivity are the most favored molecules for biosensor research. As you could see, you have gold, sometime you have used silver, eventually you will come across copper, you have nanocarbon, you have zeolite, you have MOS2, and one more added feature which could be porous. Why it is porous? Because for all these enzymatic assays, you need higher surface area to immobilize the glucose oxidase enzyme. So, the more and more glucose oxidase enzyme you can immobilize on this structure, it will improve the sensitivity of the system. So, now from here we move on to some of the schematics of the one which has been shown. So, here is the basic reaction we have already discussed, and this is what is happening at the site of FAD. So, you have synthesis of glucose oxidase and ZIF8. So, you have zinc and 2-methylamidazole, schematic display of copper nanoflower, based glucose nanobiosensors, schematic illustration of glucose biosensor fabrication, what you could see out here, where you are kind of immobilizing the whole process of how you are immobilizing the whole process, and eventually you are having the whole chip out there ready. Then section C tells you about the schematic illustration of enzymatic glucose biosensors fabrication. Part 1 is a preparation of long conductive enzyme loading hybrid nanocomposite. Part 2, we are talking about preparation process of glucose biosensors via direct electrophoretic deposition onto a glassy carbon electrode surface and subsequent photolinking. And the section D is schematic display of one-step involvement preparation of glassy carbon electrode, multi-walled carbon nanotube, ruthenium nanoparticle, and GOX biosensor. So, these are some of the basic examples of how this field is slowly progressing. There is another very interesting development which has taken place recently, which is hydrogel chitosan based glucose biosensor. So, when you talk about this hydrogel chitosan based, so most of these molecules are used for wound dressing, tissue engineering, and controlled release. So, these are molecules which are commonly known to bioengineers or tissue engineers for these purpose. But pretty interestingly, very recently, chitin, which is a polymer, chitin layer is found on the insect body. There is an enzyme called chitinase which can dissolve that, but it is a pretty strong layer. Chitin and chitosan are natural polyaminосaccharides. Chitosan is obtained by the controlled N-deacetylation of chitin. Chitosan is insoluble in water. However, the amino groups rendered it soluble in an acidic solution below the pH of 6.5. Most important, it has an ability to form hydrogels, and it is possible to produce thin hydrogen film of chitosan on solid electrode surface. So, with the electrode surface on which you have the hydrogel layer, which is extremely porous with a huge amount of interconnected network, and this is the critical point that makes it particularly applicable to the fabrication of miniaturized biosensors. Moreover, the abundant amine group of the chemical structure make it useful candidate for application where various surface modification methods are required in order to achieve immobilization of a particular biomolecule. As a result of these benefits, together with its biocompatibility and lack of toxicity, Chitosan has been widely used not only in the field of electrochemical biosensors, but also in the controlled release system, drug delivery systems, and wound dressing and tissue engineering. So, one of the work what I am going to discuss is Krishnan's work, which the next figure will give you an idea, which is utilized chitosan as an immobilization matrix for glucose oxidase enzyme. Briefly, there is palladium nanocubes were synthesized with an average edge length of 30 nanometer, and then a shell of platinum was deposited on their surface. So, it is basically, you see this palladium cubes on which you have the platinum sitting on top of it. So, this is the palladium and platinum complex. On top of that, you have immobilized glucose oxidase. The covalently immobilization of glucose oxidase on the surface of chitosan coated nanocubes was accomplished by reacting with glutaraldehyde followed by addition of glucose oxidase enzyme. The GOX immobilized chitosan coated nanocubes were then deposited on a glassy carbon electrode surface. The sensitivity resulting biosensors was determined to be 6.82 microampere. So, this is one of the another very recent development which has happened in terms of glucose sensing, basic reaction which is happening here, and you have this whole matrix. So, if you look at the whole process or the way the whole field is moving, the major challenge is are 3. So, these are enough examples I have shown you. First of all, when you are getting a sample is a mixture of n number of different compounds. Out of that, you want to detect 1 or 2. So, automatically all other molecules are interfering in the process. Now, if you want that particular molecule to come to the site where you are detecting, say for example, in this case glucose. So, you are having a urine sample, it has tons of interacting ions, other compounds, maybe some small amount of protein, pus cells and so on. Now, you want to detect glucose. So, what you are trying to do is that you are reacting glucose with oxygen in the presence of glucose oxidase, and you are getting a product in that process by the oxidation, by the reduction of the oxygen to peroxide, and you are again oxidizing it to measure the electrons which are being released. Now, in this whole process, you have to come, the glucose has to come close to the enzyme binding site, so do the oxygen. Yet there is another challenge. Even after they bind to the pocket within the enzyme, how efficiently you will be able to monitor the electron transfer reaction which are happening on that site. That is the challenge. So far we have studied multiple strategies by which you can do. You can make an apoenzyme, you can connect the FAD, or in this case FAD, the electron transfer site, directly to the electrode, or using a coupling molecule, or you can wear the whole enzyme. But you realize one thing, for all these processes you need a large amount of enzyme, in this case glucose oxidase. And pure enzyme means you are increasing the cost of the system. That brings us to a point, could we have a non-enzymatic sensor? What is the basic philosophy of a non-enzymatic sensor? If you logically think through. So, let us go back to the reaction from where we started this journey, because that is the reaction which will help us to understand that what is the unique feature of the non-enzymatic reactions. If we understand that, then rest all will be cakewalk for us. So, what exactly is happening? Let us see the reaction. Glucose plus oxygen. In the presence of glucose oxidase, we are getting gluconic acid and peroxide. So, essentially glucose is gaining electron, oxygen is gaining electron and getting reduced, right. On the other hand, glucose becoming gluconic acid, it is a oxidation process, it is a redox reaction which is happening. And then what we are doing is that we are oxidizing this, which is liberating 2 electron and 2 protons, and we are measuring these 2 electron. This is exactly what is happening. And the second reaction is happening on the electrode, where we are giving a certain kind of a potential. In this case, it is 0.7 volt. Now, think of, instead of the presence of glucose oxidase. So, we want to remove this. So, this will not be there in the reaction. How these two will react? These two have to react in the absence of glucose oxidase. That is the basis of your non-enzymatic sensor. This could happen if we bring these two molecules close enough and create a situation to, in this case, reduce this. So, we have, if we have a reducing environment for oxygen, then this reaction can happen even in the absence of glucose oxidase, and such reducing environment can be created by manipulating the voltage of, or the electrical parameters of the electrode on which you are developing the sensor. So, if you could alter the electrode parameter, are you giving it electrons or you are taking an electron from there, you actually can carry out the reaction. So, if we talk about any non-enzymatic reactions in this situation, it will have to be altered by a nano or any structure where you can alter the electrical properties of it. So, if you look at it, non-enzymatic detection of glucose or direct glucose electrooxidation. So, you are oxidizing the glucose. If you remember, it is the glucose which is getting oxidized and it is the oxygen which is getting reduced, and that is what leads to gluconic acid, and this leads to peroxide. Glucose oxidase based biosensors have been studied extensively as discussed. However, the possible decrease in the catalytic activity of the enzyme arising from the immobilization process is still a challenge for researchers in terms of performance of the sensors as well as the long stability of the desired biosensors. So, all throughout we talked about some of the finest biosensors, where there are a lot of immobilization has happened, some ultra modern structures have been developed with molybdenum sulfide, gold, silver, copper, zinc, carbon nanotubes, carbon quantum dots, but you realize when you are embedding a molecule or an enzyme into such clusters, their activity is being compromised. And in the last section I told you, you need more and more enzyme, that increases the cost. So, if their activity is going down, then your detection will be lower. So, it means your efficiency will be lower. They are all directly correlated. Now, direct electrooxidation of glucose in the absence of enzyme may provide a solution to some of the problems of enzymatic systems. This is the fundamental basics of the beginning. However, the selectivity of the catalyst developed towards glucose should be investigated in detail for biosensors is to be used in a highly complex matrix. It is noteworthy that at the time of writing, most of the enzyme-free biosensor for glucose detection exhibit sensitivities at the highest end of the scale as compared to the enzyme-based glucose sensors. So, this is where the field is going to go, non-enzymatic detection. If we have a parallel method or parallel technology which is non-enzymatic, which is not costly, which is at par of the detection limit of an enzymatic system and free from errors, efficient, that will be a breakthrough, and that is where most of the glucose sensing work is happening non-enzymatic. You do not use glucose oxidase, you do electrooxidation, or in some cases other cases electroreduction, depending on how you want to do it, but you are using an electrode to do the work for you. As long as you understand this part, rest of the electrochemistry will become easy for you. So, in the next week, we will talk a little bit in depth about the electrochemical aspect of the journey of biosensors. And with this, I close this class and we will pick up more of the biosensors fabrication, biosensor design, and the real chemistry between the electrodes, voltammogram, amperometry, and choice of electrodes. But one thing I must tell you, during last 60-70 years of this development, most of the inspirations have been drawn from this oxygen and glucose biosensing for any other sensors which have been developed. And that is the reason why I am devoting so much time, because all these materials what you see here, use of molybdenum sulfide, use of gold nanoparticles, use of carbon nanotube, carbon quantum dot, graphene oxide layer, nitrogen doped graphene oxide layer, use of boronic acid, use of chitosan related material. These all are the advancements which have been employed in any other sensors you will read. So, if you understand 1 or 2 or 3 or 4 sensors properly, then rest will be far more easier. So, that is why we are devoting time in making you understand the basics, so that you can think beyond this. So, with this I will close the class. Thank you.